Greetings, this is Artie from Artifact Electronics. In this episode we'll be looking at an HP 5300A measuring system, and this is a unit that I found at a local swap meet. It was sitting in the midst of a bunch of power tools on the ground, and the seller wasn't exactly sure what it was. And when I asked him how much he wanted, I didn't even bargain with him anymore, because I think it was like $10 or $12. And of course I had to ask him, does it work? He said, yes, I just tried it. And I said, and he didn't, of course, have a power outlet or a generator there, but for that price, I thought it was worth getting it just to be able to look inside and see what it does. Of course, the most important thing is what state is it in. I've cleaned it up as usual. It had probably been dragged from meeting to meeting and accumulated a lot of dirt on the way, but it cleaned up somewhat nicely. And here, of course, for the most important thing, and that is, does it do anything? And it does. It came up pretty much immediately. Let us short the inputs and see if it auto zeros at least. And well, pretty close. It is currently set to DC volts with a range of 10 volts, and yeah, so it seems to be doing something. We're going to have to look at, feed it some signals and see how it does. But for now, let's get a little bit into the history and description of what this unit is. So you're looking at the HP 5300A measuring system, and it's a modular system that HP brought out in the early 70s. And the heart of it is basically the top unit, which is a 6-digit counter. And that's all it does. The top unit doesn't do anything, doesn't take any user inputs. What you do is you get snap-on modules for it, and the snap-on modules specifically define what the setup does. And as you can see from the dividing line, the bottom part is the actual user module. In this case, it is the 5306A multimeter / counter module. And what you could do is buy different modules and fit them to the bottom of the counter unit. Initially they had a bunch of counters and frequency counters and stuff like that, but after a couple of years they came out with this unit, which was the multimeter unit. And another thing that they have is a battery that will actually fit in between the head unit and the user module, let's call it. It's about as high as the head unit, has handles on it, so you can take it into the field. I didn't get one, obviously, and I don't bemoan the fact, because those were really, really old battery units. And I probably won't be taking this in the field, but using it on the bench. So let's take a look inside. Well, here's the back. And it has an output for a digital recorder, and I guess voltage adjustments for the multimeter part, and fuse, and all the other things. Now, to take this apart, it's a pretty clever system, actually, toolless system. You pull out these tabs, and then the top separates from the bottom, like this. So here's the head unit, or the counter unit, and in our case, here is the multimeter add-on. So we haven't used any tools yet. Now when we look at the head unit, we can further disassemble this by bending these tabs back and lifting the PC board up. So this was their way to make things service friendly. And here's the inside. Let's try to get a different angle on it. So here's what the head unit looks like inside. I read some HP publications and where they're very proud that basically their counter unit is using a lot of HP proprietary LSIs. They didn't call them ASICs at that time, but they called them custom designed LSI chips. And they pretty much handle all of the aspects of counting an input signal and displaying it on the 7-segment displays, to which we'll get in a minute. But there's some standard LSTTL stuff here, and then all of these guys are proprietary HP chips. So I think if anything goes wrong in here, then you're done. But it's HP quality, it seems to work, and later on we'll find out how well it works. The caps are original. I'm afraid to even get close to them, but they still work. And one thing I noticed is on the other side there was a note that basically said remove screw before disassembly. And it's pointing at the screw, the hole just above the transformer, and there was no screw in there. And right underneath it in the case is actually a mounting hole for the screw. So somebody's been in here and somebody didn't put it back together well, and that's actually not a good thing to leave out, because the missing screw along with this screw is what holds the transformer laminates together. So it's extremely important to have this screw in there, because otherwise this thing's going to start buzzing. I did already look through my box of screws, and I do not have a screw that is long enough for that, so I'm going to have to hunt one down. But that's pretty much all of the bad stuff I saw inside. Other than that, you're looking at a typical HP board with the gold-plated traces and relatively clean layout. This one probably isn't as clean as some of the other stuff with the wires kind of going over the place and like over here. That's not very typical of HP, but this was a lower cost instrument. The head unit itself originally cost, they claim less than $400. And at that time, even though this was the early 70s, that still sounds like a pretty inexpensive piece of HP equipment. Now, other than that, we get to the display. It has a 6-digit display, and it's a forerunner to today's 7-segment displays. And I don't know if you remember, but the segments are actually not constant. There aren't single segments, A through G. Well, they all light up together, but it turns out that each segment is subdivided into a bunch of dots. It's more like a matrix display. And I guess at that time it was more expedient to make displays that where the segments consisted of dots rather than an entire solid segment that lit up. An interesting argument they make for this in one of the publications I read was, in case if you lose a dot in here, you're not going to get a false reading. And the way I think what they mean is, let's say your reading says 8, a digit says 8, and the center digit, or the center segment, which is segment G, drops out. Well, the 8 will show up as a 0 on regular 7-segment displays. These will mess up and they'll look funny with that dot missing, but you probably can still see that it's trying to put up an 8 rather than a 0. Well, obviously that didn't survive, and 7 segments went to solid segments, but it's still an interesting concept, and we'll look at it again later on when I plug it in. And here's a multimeter module. Also had 4 tabs over here that you could just bend back. So far I haven't had to use any sort of tool to get to where we are. Then we look underneath, and again it looks like the chips on this end are, no, they're not even LSs, they're just 74 series chips. And in order to see under this, I mean, just glancing at it from the side, there's some chips, but mostly analog components in there, and that's probably the front end for the inputs. There's some more ICs here, multi-turn pots for adjustment. But the significant thing to note is, of course, there is no processor in here. Everything is hardwired, and that's the way this works. Now, we get these 2 8 pins here, which are probably op amps. They're socketed. They also thought they needed to socket a 74L10. And I won't even guess at the reason why. Let's see if this looks like it's been replaced. And that is over... that socket is over here. Does not look like it's been replaced, so that is also the op amp. So the 8-pin chips are here, and well, here and here. That also looks factory. Oh, you couldn't even see that. Here and here, and that also doesn't look like it's been resoldered later on. So so this is all, the sockets are all factory. This chip is kind of sitting askew, it's not sitting straight. And it will continue to sit askew because I can't push it in, but it doesn't seem to have much ill effect. And again, there's some old caps over here. There's probably some more in there. Electrolytics, but and this is pretty old. But there you have it. Again, it is you know, again, it's pretty cleanly laid out. But as I mentioned before, for the head unit, it's not. This doesn't look as nicely laid out as some of the other HP stuff I've looked at, especially the spectrum analyzer. And the quality of this board, of course, is there's no gold-plated traces on this, and except this thing here, whatever that is, looks like a big question mark. And so you can see that this was more of a, they made an effort to come out with a unit that could be sold for cheaper than their other stuff, and I hope they succeeded. I had never even heard of this unit before, the 5300A measuring system, and they do pop up on eBay once in a while, but I don't think this was something that was as popular as some of their other stuff. And then again, you know, it's really, really old too. But here you have it. That's what it looks like inside. The manual for this, actually the manual for the head unit is, no, the manual for the head unit isn't available either. The way I got my information on this was HP published, I think on a monthly basis, a set of sheets that were called tech briefs that were basically updates, gave you circuit updates, and discussed the development of some of these things, and the authors and the designers spoke about them. But I haven't I haven't found any manuals or service manuals for this yet, but let me just say that if this decides to quit, and because of the number of custom LSIs on here, it's probably the end of the line for this unit if you ever get to a point where it starts quitting on you. So let's hope that it doesn't do that. Well, let's snap it back together and actually do a little bit of functional testing. So it goes back together in reverse. Let's see if that actually works. Well, it would probably help if I got the front and back right, but I think I do have it right. Yes, the tabs fit. So we press it in place, and that reassembles the multimeter part. And this is the top of the case, and this is the counter unit. So let's put the counter unit back in its slots. And that just snaps in. And the final step is, well, let's do this the right way. This goes on the bottom, and this fits into the top. So you place it on here. And push the tabs back in, and that's it. It's reassembled. So if you had an arsenal of these snap-on modules, you can see it's very easy to change them. Bench, field, anywhere else. And so let's plug it in and have a quick look. See if I can focus in on the display, and we can see the dots in the digits. So here's a close-up of the displays, and I think you can pretty clearly see now that the segments actually consist of dots, and again, I'm not sure why they went that way. I guess technology was made more sense to do it this way, even though this didn't survive the years. But it's very readable, and the fact that you can't, when you lose a segment, it doesn't falsify the reading, was actually significant, I think. What I mean by that is if you have an 8 and the G segment or the center segment goes, you get a 0. And if you're taking a reading and you don't know exactly what to expect, then it's very easy to take the 0 and enter it into your data, whereas it should have been an 8. And obviously, based depending on the position of the digit, you could be introducing some pretty horrendous errors into your readings. But there you go. The display is actually in really, really good shape. And I have no idea how many hours this was on, but it looks pretty good. So the way this works is basically the top unit is gets sent counts. And it will scan those counts and display the count on the display depending on, I guess, how fast you have the refresh rate set, which you can adjust with this button, and the flashing C will show you how quickly it's updating. So what they did is they kind of have the tail wagging the dog here, because originally they came out with a bunch of frequency counter modules, snap-on modules, so that made sense. But then of course they came up with the multimeter and went, this upper unit needs frequency. So what the multimeter actually contains is it has a voltage to frequency converter in it. So this basically, whatever reading you take gets converted into a frequency and then communicated to the upper unit. Except, of course, when you're in frequency mode, then I think it'll just take the data and send it straight up to the counter unit. So now we've set all of that. Now let's have a look and see how well this actually works. So let's start with some DC voltages. So let's get started with some DC volt measurements. I brought in the trusty Agilent 6612C DC source, and even though the output's disabled right now, I guess it is still measuring that it's outputting 12 millivolts, and looks like this guy's also saying it's 12 millivolts. So let's see if we enable the, well, let's see what the voltage is set at right now. It's set at 100 mils, so let's set that one to 10 mils. And what do I have to do here? Oh, I have to type in 0.01 and then enable the output. So now we actually know that it's outputting. Well, let's make sure that the output current isn't set to 0, because no, it's set to half milliamp. So it says it's outputting 10 millivolts, and this guy thinks it's getting 9.8 millivolts. 9.7. I think that's, I don't know what the exact tolerances are on this. I have to look that up, but that's not too bad. For something that has been around for a long time and most likely physically abused, that's actually pretty good. So let's go up by an order of magnitude. Let's go to 100 millivolts. So voltage, enter number 0.1. That's interesting. It doesn't like to show 0.1. It is set to 0.1. Oh, well, it's off. Okay, fine. That's off by 2. The Agilent is off by 2 millivolts. And in that case, the if this, if this is what's coming out of the Agilent, then the HP is off by 1 microvolt right now, or 2 microvolts. So I'd say, yeah, I'd pass that one too. Next one, we go to a volt. Well, at least this time the Agilent does say a volt. And we are off by 6 microvolts. But it's still doing remarkably well, I think, especially since it has one extra digit than the Agilent here. So for all we know, it might not even be off, because if the Agilent's rounding things up, then it's probably spot on. All right, next let's go to 10 volts. So we do voltage, enter. So the Agilent says a bunch of 9s, and so now we're basically off by 7 millivolts. The HP is off by about 7, a little less than 7 millivolts. And finally, the max that the Agilent will output is 20. So let's do the voltage and enter a 20. And we obviously exceeded the range, so let's go to the next higher range. And now we are off by about 10 millivolts. And again, as I said, I don't know the exact tolerances, but under the circumstances, I would definitely say that this passes the DC volt test. I don't have anything conveniently handy to put in more than 20 volts DC right now, But for the kind of work and measurements that I do, it's usually low voltage. So if the max error is going to be at 20 volts, I think this is something that I can actually rely on the bench. And just for interest's sake, let's see what the Fluke meter says. Let's see if I can get that in the picture here. And I'm going to measure what the Agilent outputs. And it says that the Agilent outputs exactly 20 volts. So going back in here again, yeah, we're off by about 10 millivolts. So DC test passed, and next we have AC frequency and ohms. Let's do ohms, because for the other two tests I have to drag out the function generator. Alright then, let's look at some resistance measurements. What do we have here? So Mr. Fluke thinks, he doesn't think anything. .702, and Mr. HP thinks all right. So we have 4.702 versus 4.69. Which in my opinion is more than close enough. So let's go to something a little bit higher, and this one, let's see if I can read the color code real quickly. No, I'll just let it read it. And let's see, we may have to go up. Okay. 35.6 k ohm, and 35.6. This time it matches. It matches exactly, even though this has more digits still. And because it's so much fun, let's do another couple of them. We get to this guy. And he is, that is 0.243 mega ohms. So that's 200, that's supposed to be 244 k ohm. And Mr. Fluke says, oh, it says the exact same thing. So they match on this reading. And finally, let's take a 1 meg resistor, 1052, and Mr. HP says 1052. Oh, just drifted. Come on. So that's off 1052. That's off what, 8 micro? No, not 8 microohms. 800 ohms. Am I saying this right? Yes, it's off 800 ohms on the 1 mega ohm reading. So I think I'll pass the ohms ranges too. So we passed ohms and we passed DC volts, and now let's bring on a signal generator to test the remaining two ranges. Alright, let's test out the frequency, and for that we're going to need Mr. Noisy's help. And Mr. Noisy is a 3314A function generator. And so let's start at 10 Hertz. That's a good place to start. I'm sure there's a way to enter this through some sort of a keypad thing, but there's numbers on here. I probably could, but it's quicker to do it this way before having to figure that out. So we're outputting 10 Hertz. Set the amplitudes at 1 volt. That's pretty ideal. There is no offset. And I'll also give it a square wave. And of course, in order to measure it, we need to switch to frequency. So there you go, 10 Hertz, measured as 10. Let's jump up an order of magnitude. And 100. Yeah, I really got to figure out how to do this with numeric buttons, but there's 1 kHz, and it's running over a bit. Okay, 10 kilohertz. It's a little bit low. 100 kilohertz. One megahertz. And also keep in mind that the upper limit of this is 10 megahertz. So it's not measuring that. So what we need to do is kick it into fast mode. When we kick it into fast, because it's not able to take enough samples when it's in normal scanning mode. So when we kick it into fast mode, then it can actually go ahead and count the 1 megahertz. And finally the 10. And 10 slightly exceeds, of course. Let's see if we change ranges. So let's lessen it a little bit, because we're probably hitting the upper limit, or that isn't going to make a change. So let's shave off a few. So let's go to 9.9. Still reads 9.9. 9.95. 7. 8, 9, so when you approach it slowly, it actually does. It switches where the decimal point goes, but it's reading 10.36 megahertz. So yeah, it's beginning to error out a little bit on the upper ranges, but if we dial that back, it's still pretty accurate on the lower ones. Turn off fast. Of course, then it can't keep up anymore. It's missing pulses, but we put the fast back in, and it's on pretty good. It starts to get a little inaccurate when you're hitting the uppermost limit, but considering that, you know, at 9.9, it's still reading 9.9 accurately. So I hereby declare that the upper limit is, well, wait a minute, let's try that. Okay, I hereby declare that the upper limit is 9.99 megahertz, and that test's passed. And finally, to the AC test. We got the amplitude set to 1 volt. And what is the RMS value supposed to be, boys and girls? It is supposed to be 0.707. So let's enable the sine output and wait an appropriate time, and there you go, 0.7084, a little above, but that reading's okay. 2 volts, of course, is twice of that, which is 1.414. And it gives us 1.408. And if we double that again, we should get 2.82. Oh, almost had it. 2.81, 2.82. And I thus declare the AC test as passed. And thus, I think this guy has passed all of the tests. And I can declare him fit for use on my bench. Finally, I wanted to share the rather humorous title of one of the bench briefs from HP on this instrument. The Lilliputian measuring system does much and costs little. So I guess in those days this was considered to be Lilliputian, and so I'm not exactly sure what you would call this in terms of scale, but if you have any good ideas, leave me a comment. Anyway, we're at the end of this, and I hope you enjoyed it, and please leave the appropriate thumbs up and click the subscribe, and we shall see you in the next exciting episode, so catch you on the flip side.